Hey guys, Mr. McKinney here, just talking about more related rates, which basically just means word problems with implicit differentiation. All right, so let's get started. The first thing we want to talk about is what you're taking the derivative with respect to. So if we start with this problem, 2x to the fifth plus 4y cubed equals 4. First, we're going to look at dy dx, and then we're going to look at dx dy, and we're going to look at how they're related. So if I want dy dx, the variable on the bottom tells me what we're taking the derivative with respect to. So I need to take the derivative of each term with respect to x. So to take the derivative of 2x to the fifth with respect to x, that's what we're used to doing. So move the 5 in front. We're going to make it 10x to the fourth. And then the derivative of x with respect to x, you don't have to write this, but you can, and it's going to go away. That's just 1. Now, when I take the derivative of y with respect to x, that's where we're going to get our dy dx. This is the derivative of y with respect to x. So for this next term, I would get 12y squared times the derivative of y with respect to x. Dx dx cancels out. That's just 1. Dy dx does not cancel out. This is what I'm solving for on this problem. And then the derivative of a constant with respect to x, doesn't really matter what it's with respect to, the derivative of a constant is always going to be 0. So now I'm trying to solve for dy dx. So the first thing I would do is subtract this 10x to the fourth term over. So 12y squared times dy dx equals negative 10x to the fourth. And then I could divide both sides by 12y squared to get my dy dx term by itself. So I'd have dy dx equals, I'm going to reduce the negative 10 over 12 to be negative 5 over 6. And I've got x to the fourth over y squared. So dy dx would be negative 5x to the fourth over 6y squared. The rate of change of y with respect to x can be found by this equation. At any given point, I would have to plug in an x and a y to find the slope. All right, now let's look at if I flip these upside down. So what is the rate of change with respect to y? So again, the variable on the bottom is going to tell you what you're taking the derivative with respect to. So in this problem, I want to take the derivative of everything with respect to y. So in this first part, we're going to start out with the power rule. So 10x to the fourth, but now I'm taking the derivative of x with respect to y. So the derivative of x with respect to y. This does not cancel out on this one. But when I take the derivative of y with respect to y, I'll get the dy dy and that'll go away. So over here I would get 12y squared and then the derivative of y with respect to y. Again, we're basically just doing the chain rule here. So the derivative of y with respect to y. Dy dy is just 1, so that goes away. And again, the derivative of a constant is 0. So now I'd have 10x to the fourth dx dy plus 12y squared equals 0. This time I'm trying to solve for dx dy. So I'm going to subtract the 12y squared over. So 10x to the fourth dx dy equals negative 12y squared. And then I'm going to divide both sides by 10x to the fourth. So my dx dy term, again, I'm going to reduce this. So I'd have negative 6 over 5 y squared over x to the fourth. Notice that again, my term for the slope has both x and y in it. And this would be the rate of change of x with respect to y. When we think about slope, normally we're thinking about the rate of change of y with respect to x, which is what we found on the first problem. Now let's look at how these two answers compare. So dy dx and dx dy. And if we look at them, they're almost exactly the same. The only difference is that we have flipped it. So to get from dy dx to dx dy, I've literally just flipped the numerator and the denominator. This is always going to be true. So if a problem asks you to find dy dx and then later asks you to find dx dy, you don't have to go through all the work again. Just find your answer for dy dx and flip it. So you're allowed to do that. If you found one and you need to find the other one, you can just flip it. You don't need to solve for the other one independently. All right, now let's make it a little bit more interesting by adding in another variable. So I want to find dy dt when x is 1 and when dx dt is 5 for this equation, y equals 2x cubed plus 3. So this is the equation that I'm starting with. Y equals 2x cubed plus 3. And I want to find dy dt. If I just took the derivative and made it 6x squared, that would be finding dy dx. So in order to get dy dt, I need to take the derivative of everything with respect to t. And when you see the d, whatever letter on the bottom, that's going to tell you what we're taking the derivative with respect to. So on this problem, I need to take the derivative of this equation with respect to t, even though t is not in this problem. And that's okay. You can take the derivative with respect to whatever variable you want. So I want to find the derivative with respect to t on this problem. So the derivative of y with respect to t is dy dt. That's what I'm looking for. The derivative of 2x cubed with respect to t, so I'm going to do the power rule, 6x squared, but then I need to do the derivative of x with respect to t. dx dt is not going to cancel out. Derivative of a constant, that still goes away. So I have dy dt equals 6x squared times dx dt. This is my equation, and they've given me some information. They've said x is 1 and dx dt is 5. So now I can plug these things in. So dy dt equals 6 times 1 squared times 5. dx dt is just 5. So 6 times 1 times 5 is 30. So dy dt would be 30 when x is 1 for this equation. So again, you can take the derivative with respect to whatever variable you want, and just look at the bottom of the fraction to figure out what variable you should be taking the derivative with respect to. All right, let's look at another example. So I want to find dy dt when x is 3, it gives me dx dt, and then it gives me another equation. The similar idea, but I'm going to have to use the product rule here because I have x squared times y. So let's rewrite it over here. X squared times y equals 81. All right, so I'm going to have to use the product rule. And again, we're going to take the derivative with respect to t. Now, in theory, you could solve for y and then use the quotient rule, but it's a lot easier to just use implicit differentiation and take the derivative of everything with respect to t. So my u would be x squared, my v would be y. And let's see what u prime and v prime would be. So the derivative of y, if it was with respect to x, would just be dy dx, but we're doing it with respect to t, so the derivative of y should be dy dt. Now over here, when I take the derivative of x squared, it would be 2x, and then the derivative of x with respect to t. So make sure you have a dt term in both of these. Derivative of x squared is 2x dx dt. Derivative of y is dy dt. All right, so now let's use the product rule. So v times u prime plus u times v prime. So v was y times u prime was 2x times dx dt plus, and then u was x squared times v prime was dy dt. And then the derivative of a constant is 0. All right, let's plug in what we know. We know x is 3, we know dx dt is -6, and we're trying to find dy dt. So this is what we're trying to find. Now the other thing is, I don't know what y is, so I'm going to have to use x with my original equation and figure that out. So off to the side, we're going to say x squared times y equals 81. When x is 3, 3 squared times y equals 81. So 9y equals 81, which means that y equals 9. So off to the side, I'm going to have to figure that value out because I need y to plug into this equation when I'm solving for dy dt. So sometimes you're going to have to use the x value to figure out the y value, or you could have a y value to figure out the x value from the original equation. You won't know if you need it yet or not until after you've done the implicit differentiation to see if you need the actual value or not. In this case, we do. So let's start plugging things in. Y is 9 2x would be 2 times 3. dx dt is negative 6. X squared, so 3 squared. dy dt is what I'm solving for. So I need to make sure that I was able to plug in for everything except for dy dt. So 9 times 6 times negative 6, I'm just going to leave it all the way it is because it's going to be able to cancel out in a second. So I'm going to add that over to the other side. Let's start here. So this would be 9 dy dt. If this would be a negative, so when I add it over to the other side, I'm going to get 9 times 6 times 6. That way, when I divide by 9 here, these 9's cancel out, and dy dt is just 6 times 6, which is, whoops. All right, whoa. Let's just write it up here. dy dt would be 36 on this problem. So again, I had to implicitly differentiate. I used the product rule, and then I had to go back to the original equation to find the y value that corresponded with the x value that they gave me on this problem. All right, here's a whiteboard practice problem. So hit pause, give it a shot, and then we'll go through it together. All right, so let's see how you did. So I want to find dy dt. It gives me an x value, it gives me a dx dt value, and it gives me an equation. Let's start with this equation and take the derivative with respect to t. So x cubed plus y squared plus 2xy equals 16. Taking the derivative with respect to t. So over here, I'm going to have 3x squared dx dt. And then 2y dy dt. For this part, I'm going to have to use the product rule. So I'm going to say y times the derivative of 2x, which would be 2 dx dt, and then 2x times the derivative of y, which would be dy dt. Derivative of a constant is 0. Now let's start plugging some things in. Now I do have a y in this equation 2 times, so I'm going to have to figure out what y is also. Let's do that real quick. So I'm going to switch colors. Let's go to yellow. So if I plug in 1, actually yellow is not showing up very well. Let's switch it to green. So if I've got 1 cubed plus y squared plus 2 times 1 times y equals 16. So really I'm going to have y squared plus 2y. 1 take away the 16 would be minus 15. So I'd get y plus 5 and y minus 3. So when x is 1, there's 2 values that y could be. Y could be negative 5 or y could be positive 3. And we're going to have to look at both of those cases. All right. And so at this point, you can either start plugging in values and do it twice, or you can solve for dy dt. Since I'm going to have to plug it in twice, I'm going to go ahead and solve for dy dt in terms of x and y. So dx dt I can plug in. So 3x squared dx dt is 24 plus 2, and then I'm going to leave it as y for now, and dy dt is what we're solving for. Y I'm going to leave as y, so again I've got 2y, and then dx dt we have in the problem was 24, 2x, and then dy dt again. Notice that this is a plus. All right, I'm running out of time on this video, so I'm going to hit pause and work out some steps and then unhit pause. All right, definitely needed more space, but here are the 2 answers. So at the point 1, negative 5, the rate of change of y with respect to t would be negative 21. At the point 1, 3, the rate of change of y with respect to t would be negative 27. You can kind of see my work here. Feel free to email and ask questions if you have them. Basically, I plugged in 1 and negative 5 into this equation and solved for dy dt over here. And then I plugged 1 and 3 into this equation and solved for dy dt over here. So there's 2 answers because there are 2 points when x can equal 1 on this equation. So if I graph this, there's 2 values where x is 1, 1, 3, and 1, negative 5. So I can find the rate of change of y with respect to t for both of those. Hope this helped.